Hello, we're going to simulate a flexible string with a resonant bounding condition. This is designed to approximate the behavior of a string attached to a resonating soundboard, as in a guitar or a piano. The flexible string has a natural frequency of 200 Hertz, which is near G3 on the piano. It is 1 meter long, and it is going to be plucked at 1/9 of its length. The bridge in the soundboard is going to be simulated by a spring mass dashpot combination, and we're going to have 3 different natural frequencies for that spring mass dashpot. One that's less than that of the spring, one that's greater, and the other is also greater. Here is a schematic of the process that we're going to simulate. Here's our bridge soundboard over here with the spring and the mass. It's described by this differential equation, where the frequency, the natural frequency is determined in terms of the spring constant and the mass. The string is described by this differential equation, and there's the natural frequency. Okay, let's start the simulation now. Here's the first case when we have the resonant frequency for the board of 100 Hertz. Watch the red circle over here, which is the actual magnified position of the soundboard. It's magnified 10,000 times. The position also is indicated by the end of the blue line here, but because of the scale here, you can't see that move. All right, let's take a look at the picture of the variation of the soundboard with time. Here we have the amplitude of the soundboard versus time, 150 milliseconds of simulation. And here is the spectral picture of that. We have a strong component here at the fundamental of 200 Hertz. The contribution at the partial of 400 Hertz, a little bit at 600 Hertz. Here's a contribution from the soundboard at its natural frequency of 100 Hertz. Here's the cumulative spectrum, and it shows that around 95% of the signal power is at 200 Hertz. There's about 5% at the soundboard natural frequency, and maybe 1 or 2% at the partial at 400 Hertz. Okay, let's do the second case here, where we have a natural frequency for the soundboard of 300 Hertz. The shape of the wave as it propagates back and forth is pretty much the same. The movement of the red circle is a little different because we have a different resonant frequency for the soundboard. Here is a picture of the soundboard movement for 150 milliseconds of simulation. And you can see the periodic component here is a little bit different than before, as indicated by the spectrum. Now we have still have power at the fundamental at 200 Hertz, but there's a lot more power here at the partial at 400 Hertz and a little bit of power here at 600 Hertz. The soundboard is represented by this power here at 300 Hertz. The cumulative spectrum shows that now we have 70% of the power at the fundamental, about maybe 12% at the soundboard natural frequency, and about 15% at the partial at 400 Hertz. Now, in the last case, we have a natural frequency of the soundboard at 500 Hertz. As before, the wave shape is pretty much the same. The movement of the red circle is different over here because of the different natural frequency of the soundboard. Here's a picture of the soundboard movement, different from the previous cases as you might expect. And here's the spectral picture. Here we have a lot of power at the harmonic at 400 Hertz, not so much at the fundamental. Got some power here at the 300 Hertz point, which is the soundboard natural frequency, and some power here at the 600 Hertz partial. Here's the cumulative spectrum, which shows that only 20% of the power is at the fundamental, about 50% is at the harmonic at 400 Hertz, maybe 10% at the soundboard natural frequency, and maybe 12% at the 600 Hertz partial. Now here is a picture of the 3 spectra for the three different cases, 100, 300, and 500. And while we're looking at that, I'm going to play the sounds of the soundboard. In other words, the sounds associated with the pictures we showed earlier of the movement of the soundboards. First, the 100 hertz case. Now 300 hertz. Finally 500 hertz. You see those are different. They sound differently because the power is distributed differently over the various frequencies. Let's listen to it again.